The Industrial Revolution was, above all, the story of coal and what people were able to do with that coal. Coal changed life tremendously.
Because when you think up until 1698, all physical work done in the world was done by man, assisted by animals, and then a little bit later by windmills and water wheels. That was all they had.
Today, we have a lot of options, not just coal, but nuclear, natural gas, renewables.
There's more coal being burned today than ever in the history of the world.
Coal has been incredibly valuable to the society we know today. It's also caused a lot of problems.
If we want to maintain the Earth habitable for humans, then we have to reduce our carbon emissions drastically.
China and India, with a huge demand for energy, that energy will be supplied by the most accessible and the most affordable fuel that those societies have to access. And that's going to be coal.
Funding provided by the U.S. Department of Energy, Office of Fossil Energy, the National Energy Technology Laboratory, members of the Energy and Environmental Research Center's Plains CO2 Reduction Partnership, and the members of Prairie Public.
Our modern way of life did not happen overnight. We needed a lot of energy along the way, starting with coal. Developing nations are looking to attain the same quality of life, and that means the world will be consuming a lot more energy. Everything from alternative energy to fossil fuels, including coal, our original source of concentrated energy. Looking back, historians can pinpoint where the seeds of modern life took root.
An industrial revolution, that is a really profound technological shift which changes the way that people live, communicate, transport, produce things in the economy. Before we had industrial revolution, people lived in the countryside, they had very short life expectancies, they were very constrained with the amounts of energy that they had at their disposal. Everything basically come from the sun, direct solar energy in the form of eatable plants or forest products, or some wind power and water power, and animals could work for them. They couldn't really increase their level of income very much or their energy consumption very much.
In England, a growing population demanded more energy for household and industry, at the hearth and at the forge. Wood was scarce, but they had coal.
Coal was vital for Britain long before the Industrial Revolution, long before the mid-18th century, because all our woodland was depleted, mainly for turning it into agricultural land. In this country, coal was important for blacksmiths, heating houses, and so on.
Britons began digging up the coal exposed on the surface, and then followed the coal layers into the hillsides. By 1700, some of Britain's coal mines had reached depths of hundreds of feet, and horse-powered water pumps ran night and day to control seepage. One man, Thomas Newcomen, was looking for a cheaper way to pump water, but his invention needed better quality iron.
Iron smelting required charcoal. Charcoal provided heat and the carbon needed to extract the iron from the ore. You could only make a little bit at a time, so iron products were very expensive.
Charcoal came from dwindling supplies of wood. By 1709, Abraham Darby was using coal as the source of both the carbon and heat in the smelting process.
Abraham Darby began using coke in place of charcoal. Coke is coal that's been baked to remove tars and other impurities. He was able to make high-quality cast iron in larger batches, increasing the efficiency and reducing the cost.
Just 3 years later, in 1712, Darby made cast iron parts for Thomas Newcomen's first commercial steam engine.
The first major use of coal industrially was with a Newcomen steam engine. You heated water, filled a cylinder with steam, cooled the steam, created a vacuum, and the cylinder pulled down. And they used for pumping water out of mines.
The Newcomen steam engine was cheaper to run than horses. By 1760, more than 100 steam engines were pumping water out of mines across Great Britain, using cylinders cast at Coalbrookdale. These new ways of using coal sparked the Industrial Revolution.
The steam engine was a sea change in energy use. For the first time in history, humans are using energy from heat to power a machine, burning coal to make something move. It's a completely new way of using energy.
Starting in the 1770s, James Watt made several improvements to Newcomen's steam engine.
James Watt increased the efficiency of steam engines hugely from Thomas Newcomen's engine, so he doubled the power of steam engines overnight. Great for fuel economy. Wouldn't burn so much coal to do the same job.
Now, more mine owners could afford to replace muscle power with machine. By 1790, the Industrial Revolution was gaining momentum. James Watt and his partner Matthew Boulton were producing coal-fired steam engines to pump water out of mines and even power a textile mill.
First Industrial Revolution is centered around coal and what people were able to do with that coal, which was the steam engine, and also the innovation of how to use coal to produce cheap metals.
By the 19th century, steam engines were driving a fair old bit of industry, but watermills, windmills were still quite common, and so were animals. So gradually steam took over. It took over more gradually than people realised because it was expensive. And one of the great things about the Boulton and Watt steam engine was it used much less coal. It was more efficient than the others.
Demand for more steam engines meant demand for more iron and more coke. As coke was produced, waste gas was generated. Over time, technology made this flammable coal gas a source of light.
Well, Britain in the early 1800s, before gas lighting came along, was a very dark place indeed. The big breakthrough, of course, was coal gas in the early 1800s, and it suddenly lit up the street. Gas lighting brought about a revolutionary change, really, in nighttime in Britain.
Coal gas began to light up streets and factories. The first gas companies were established in London in 1807 and in Baltimore, Maryland in 1816. Beyond Baltimore, few Americans had experience with coal at the beginning of the 1800s. That would soon change in urban homes.
Right around the time of the War of 1812, what we start to see is a bit of a transition in home heating from open fireplaces to stoves. At first, these stoves would have burned wood, but then as firewood became more and more scarce, they started to burn coal. That was a period in which you had major fuel shortages. And it was because the country was running out of firewood for American cities. And so it's at that time that you see entrepreneurs begin shipping their coal to American consumers for home heating. Coal becomes the preferred home heating fuel because it was a lot cheaper and a lot more reliable than firewood. It's really home heating that begins this long association of Americans with cheap, abundant, and available energy.
Demand for coal grew as more cities were lit with coal gas and more homes were heated with coal stoves. But demand would reach a whole new level once innovators on both sides of the Atlantic found a way to make the steam engine mobile.
The railways were really the result of tens, even hundreds of years of industrial development. So to get an engine on a track requires all sorts of technological advances. So you need the steam engine to work properly, you need a track that is properly laid and is stable, you need a way to connect the steam engine with coaches and so on. So they weren't invented in one go. They were a whole process of development that finally came to fruition with the railways of the early 1830s in both the United States, in England, and also in several European countries. The railways grew incredibly fast. Within 20 years, there were 6,000 miles of railway. In Great Britain, this same process happened in the United States. Again, within 20 years, there were thousands of miles of railway. Railroads created the economies of the capitalist countries. It wasn't a kind of coincidence that, capitalism and rapid economic growth takes off as the railways take off. They were the engines of economic growth.
The growth of railways required more coal for making iron and powering the locomotives. And every bit of that coal was dug by hand. In America, by men and boys. In Britain, by entire families.
The man of the house would actually take what they call a pitch or a stall in a working pit, and he would be responsible for getting all of the coal out of there, hacking away with the pickaxe. The wife, or what they'd call the hurrier, she'd actually be dragging the coal out, sometimes on a railed trolley, and you'd have the younger members of the family might be helping to load the coal once the father's hacked it out, or to open and close the air doors. So they'd be working as discrete family groups. There was no sort of safety regime. Ventilation had to rely on natural air currents. So as your colliery got larger, you'd end up with build-up of gases such as carbon monoxide, carbon dioxide, methane, which is an explosive gas. It was really hell on earth, or hell under earth, you could say, I suppose, really.
Coal was becoming the dominant energy source in Great Britain. By the 1840s, British miners were digging half of the world's coal production. While coal-fired steam powered industry in Britain, the fledgling industry in America developed using the resources at hand. Textile mills in the first factory town, Lowell, Massachusetts, developed around running water.
The whole reason that Lowell is here is the water power system. The Merrimack River, in the space of about 1.5 miles, drops 32 feet. And that drop is what powers these mills. Lowell is one of the most important cities in the American Industrial Revolution. It's really the first large-scale industrial city built solely for the purpose of producing cloth and producing profit for the mill owners. So this is really where industrial America begins. They noticed as they were building more and more factories that they were starting to run out of water. The mill owners, they need some kind of backup source of power, and they turned to steam.
In 1849, George Corliss of Providence, Rhode Island, patented refinements to the coal-powered steam engine. It was especially suited for the textile industry.
Now that steam power is interesting because, well, once you can put a steam engine in there fairly cheaply, well, now you can put a factory anywhere you want. And factories begin to grow up right along the coast where they have easy access to both the coal coming in to run the steam engines, but also to be able to ship out their textiles.
And so what coal does is it essentially allows industrial production to be both concentrated and it liberates it from sources of energy like water, wood, and wind.
Demand for coal was growing.
By the 1860s and into the 1870s, most Americans living in northern cities would have been burning coal. Once people become dependent on the pretty steady and efficient heat that coal provides, what they found was any disruption in that supply seemed chaotic.
Much of that coal had been coming from Pennsylvania, but that was changing too, as the steam engine on wheels covered more ground.
What we start to see is the emergence of essentially a national grid of coal production linked together by railroads to the point where if you were in Chicago and you were a consumer in the 1880s and 1890s, you could burn coal from any number of sources. What this meant for American coal consumers were relatively low coal prices. Railroads had an impact on so many things. First and foremost, railroads literally shrunk time and space. The cost of shipping goods declined dramatically because of railroads. Railroads created an environment that encouraged technological and organizational innovation.
While railroads were building the delivery network for goods and energy, coal was providing energy and raw materials for infrastructure. Millions of tons of coal were pouring into Pittsburgh. The reason was steel.
Iron's a wonderful metal. You could build a number of things out of it, but it's very brittle. Steel, on the other hand, is very malleable. You can make whatever you want out of it, and it maintains its integrity. Steel's not a naturally occurring element. It needs to be made by man. So you have to make iron first. And to make iron, you need coke, iron ore, and limestone. We sit on the Pittsburgh seam, which is one of the richest coal seams in the world. You have rivers for transportation. You have the Pittsburgh seam providing coal and coke. Then you've got iron ore in this region. You've got limestone in this region, and you also had an immense amount of capital. You couple that with all the raw materials, you've got everything you need for successful industry.
Ovens ran night and day, making coke from the coal of the Pittsburgh seam. Thousands of rail cars transported the coke to iron smelters and steel mills. Scottish-born Andrew Carnegie was the driving force behind the Pittsburgh steel industry from 1874 to 1901.
They were producing structural steel. Plate from this mill went into Panama Canal locks, all the skyscrapers, numerous structures all over this country that allowed America to move into the 20th century.
Like steel and textile mills, coal mining itself was undergoing changes as industrialization demanded more and more energy.
There's more technology applied to coal mines in the period after the Civil War, more sophisticated steam engines, more sophisticated notions of ventilation. They're making it more of a kind of factory type of operation. By the 1880s and 1890s, you would have had miners that did one or two jobs. So it would have mirrored the kind of division of labor that was occurring up at the surface in American factories. There's also a greater application of technology to mining, so that by the 20th century, it's still a very dangerous workspace, but would have become much more technologically advanced.
More and more cities were taking advantage of easy access to coal. By the late 1800s, nearly every city had its own coal gas manufacturing plant.
These were pretty much one gas plant at a time for each city or each urban area because they couldn't distribute their gas very far. It was quite, I think, an honor to have one because it was showing some advancement of the city.
Although coal gas was originally used only for street lighting, technology now brought coal gas into urban homes too.
The gas manufacturers tried to find other markets, and in particular they found lighting and cooking in homes to be of value. Both businesses and homes, in fact, saw that value. The market and the ability to get the gas from the plant to the end users was how town gas set the stage for natural gas.
Better than candles and more convenient than the coal stove, coal gas contained toxic gases that could be a problem inside the home.
Town gas is actually a mixture of carbon monoxide, hydrogen, and methane, and it also contains some amounts of carbon dioxide, hydrogen sulfide, hydrogen cyanide, and nitrogen. New technology developments come with a cost and a benefit. I mean, if you think about it, town gas brought safer streets because they were lit. It brought quality of life improvements to homes for cooking and lighting. And it brought jobs to the local community. At the same time, it did cause odors. It did result in these discharges to the waterways. Things that the public would react to and file nuisance suits. The industry was being regulated through the states and localities based on these nuisance complaints. There really weren't federal environmental regulations.
Nuisance suits spurred research. What had been waste became the source of valuable products.
The major byproduct called coal tars is substitutes for paints to make a water-repellent felt roof. They were used for waterproofing ship bottoms, waterproof fabrics, and they were used to pave roads. The British found out that certain components of tar, in particular something like a compound called aniline, could be used to make dye. And the tar became a really valuable byproduct and actually became the beginning of an industry essentially in the 1880s. This provided numerous types of chemicals to make things from drugs to disinfectants to perfumes to explosives. Creosote is in fact a fraction of coal tars. Creosote is used extensively for electric poles and railroad ties. There are still wood treaters today that treat their wood using some creosote.
Even as Carnegie was building his steel empire, another transformation related to coal was already underway. A new energy carrier, electricity.
When electricity first came out, people went, hey, this is cool, what do we use it for? The first use of electricity was for light.
The little incandescent electric bulb. It was invented more or less simultaneously by Joseph Swan here and Edison in America. And eventually they had a joint company called Ediswan. And this little lamp has a little filament in it which needs an enormous amount of power to make it glow. And if you've got lots of them, you need much more power.
Right from the start, electricity came from the energy in coal.
In a very real sense, electricity as an energy carrier comes right out of steam engine technology. Edison was burning coal to make steam to spin the magnets that generated electricity for his first demonstrations of electric street lighting in New York and London in 1882. Other innovators applied the technology of electrification to other uses, just as the original water-pumping steam engine was modified to run textile mills and locomotives.
Electric motors spread faster than electric lighting.
Electric motors first started just as a demonstration, powering small trains. As people saw that, they recognized the potential of using electricity. Elevators were created because we could use an electric motor to move something from one floor to another. The subways were some of the first uses of electric motors. Paris had subways run by electric motors.
The biggest impact of electricity in the early days was the electrification of the trams, because a lot of cities at the end of the 19th century had horse-drawn trams on rails, or streetcars. And when these were electrified at the turn of the 20th century, they were much more efficient, much cleaner, and that was probably the first mass experience of electricity. Electric motors came in America much more rapidly than in Britain. In factories, you had a series of fan belts run off a central rod, which was steam driven, which drove all the machinery. This had to be replaced. So there was a big investment in getting in electric machinery.
Because of the high cost, demand for electricity grew slowly.
By 1900 in the United States, energy markets were really dominated by the fossil fuels. The American industrial economy, the large cities would have been utterly dependent, to the point where shortage of coal would have been devastating for a city. We really start to see that dependency on fossil fuel that characterizes American society really throughout the 20th century and into the 21st century.
When you think about coal, certainly from about 1850 through to 1950, there's nothing you could do that didn't involve coal. If you wanted to go on holiday, it powered your train. If you wanted to have a hot bath, it heated your water. If you wanted to flush your toilet, that fresh water would have been pumped by a steam engine at your local waterworks. Baking, coal-fired ovens. Even when you look at streets and lighting, gas lighting, all made from coal. So you couldn't live without coal.
Coal was powering the economies of Britain, continental Europe, North America, Japan, and Australia, as these coal-rich countries adopted the technologies of the Industrial Revolution. For the first time ever, coal supplied half the energy consumed on Earth. Coal use continued to grow, but as new demands for energy arose, oil took on a larger role.
An internal combustion engine is just a progression of a steam engine. In the early days, almost all automobiles were handmade. They were built in small shops, made them very expensive and very hard to get.
In October 1908, the first Model T rolled off Henry Ford's assembly line into a world of coal-fired steam locomotives, electric streetcars, and horse-drawn wagons. With innovations to his assembly line in 1912, Ford made an affordable product aimed at the masses. The energy market expanded as demand for petroleum took off.
The internal combustion engine's main impact is in transportation. It suddenly made point A to point B a lot closer than it was. The internal combustion engine even made it into the airplane.
The affordable gasoline-powered automobile was so successful that by 1930, demand for oil had tripled. At the same time, technological advancements were making electricity more useful and more available. Demand for coal increased.
Initially, electricity was entirely for the upper classes. If you generate electricity on a small scale, it's very expensive.
Over time, we figured out that it's a lot more cost effective to make power in bulk in one place and effectively ship the electrons around to lots of different people at their homes and at their businesses. So over time, you would get a city that would have its own small grid, and then those cities were all connected to one another.
If you look at the way domestic appliances came in, the first really popular thing was the electric iron. They would unplug the ceiling light bulb and plug the iron into the ceiling socket. You didn't necessarily have a power socket. It came in bits and pieces like that. Once electricity had become widespread with the grid built, then electricity began to become relatively inexpensive, and nearly all of it in Britain was produced by power stations running on coal. So coal was absolutely vital.
In America, local resources like oil and massive hydroelectric projects began meeting some demand. But coal-fired power plants generated half the electricity for the country's industry, businesses, and homes. As electricity was competing with coal gas technology for in-home lighting, a new primary energy source began replacing coal gas across America. High-pressure pipelines installed during World War II made long-distance transport of natural gas possible.
A network of pipelines provided that natural gas all around the country. And when the gas plants would finally be displaced, depended on how far it was from the natural gas. So in effect, it moved from west to the east as natural gas got piped to those areas. The manufactured gas or town gas was displaced.
Natural gas contained more energy and burned cleaner than the gas manufactured from coal.
You have to actually use less to get as much energy. And so in effect, as this higher value gas became available, it made the manufactured gas less desirable.
In just 50 years, global consumption of coal had more than doubled. But in the face of growing demand, technical innovations brought large-scale hydroelectric, oil, and natural gas into the energy marketplace.
If we look at home heating after World War II, what we really see is the rise in gas heat, a rise in people having oil furnaces in their house. And that represents a major break with the long tradition of the old-fashioned hearth, but also the industrial hearth.
Industry was also adapting to energy diversity. Railroads were moving to hybrid technology, diesel-electric.
Steam-powered required carrying vast amounts of coal or wood. With the advent of electric motors, we had something that was much more efficient, much smaller. In diesel locomotives, the diesel fuel runs a generator that runs the electric motor that is used for the propulsion of the locomotive.
Steam technology was both quite expensive, quite dirty. It took about 50, 60 years, but really by, say, the end of the 1960s, there were very few.
The railroads weren't fueled by coal anymore, but they still carried coal for industrial boilers and electricity generation. But I think our awareness of coal as an energy source really began to fade as we adopted these other fuels. Coal became a hidden fuel, a forgotten fuel in our society.
Plentiful energy, consumer choice, and rising standard of living were bringing new perspectives to the industrialized world. In 1969, cameras on the Apollo 11 moon landing mission brought home images of our finite planet.
In the United States, we used these energy sources, we developed this technology, we developed our economy. And then we started to really develop an environmental consciousness as well. And we started to look at what are the environmental effects of this rapidly developing economy and technology system. And we started to say, hey, look, there are negative consequences. We don't want to give up our energy, but yet we need to do it in a cleaner way. And that was really a pivotal moment in our culture.
We had Earth Day, which was April 1970, and the US EPA was created. And with that creation, there became an entire rash of regulations, federal regulations, like the Clean Air Act of 1970, the Clean Water Act of 1972, the Resource Conservation Recovery Act of 1976.
Coal was essential for industrial furnaces and nearly half of the U.S. electricity generation. But those major stationary industrial chimneys were a big part of America's air pollution.
The initial concern, of course, was about acid rain. So the control of the sulfur dioxide emissions has been something that utilities have been addressing for now decades. The standards have been getting tighter and tighter, plus environmental regulations have been changing concerning the solid particulates. There's been a lot more research and development of the equipment that's necessary to add to a power plant for capturing that. Then you add something like mercury. Those challenges have been repeatedly met and often at less cost than was estimated at the outset.
With technical innovation, the black smoke from burning coal was replaced by the white of condensing steam from the furnace chimneys and water cooling towers. Surface mining had taken on a larger share of coal production as new coal fields were developed after World War II. They, too, were coming under new federal regulations.
Before the 1970s, some mining companies reclaimed the land, but most did not. There was no standard. The Surface Mining Control and Reclamation Act of 1977 set standards for mine drainage and cleanup.
Mine reclamation is both the process of reclaiming the land after you've extracted the coal, and there's also final mine reclamation when you go back and clear out every bit of evidence that mining ever occurred on the site. It's a very carefully thought out and orchestrated process of filling the hole where you've removed the dirt and then the coal. So you put back the subsoil and then you return the topsoil into the same location as topsoil. Today we use technologies like GPS systems on individual pieces of earth-moving equipment so that we can return it to darn near exactly the same topography it was before.
As technology has changed, so has our knowledge of how to accomplish a safe environment. But we've learned about how to control roofs. Roof bolting systems have improved. The use of the mapping underground using GPS and lasers has enabled mines to plan to stay away from stuff where there could be crumbly roofs and so on, and go where the coal really is. On the surface, the safety techniques more resemble what you find at a construction site. It's all about heavy equipment and being sure which direction vehicles are running and the normal things.
Other regulations addressed environmental concerns at industrial sites that were no longer in use. Town gas sites were a special challenge addressed with the Superfund Act of 1980.
It was the one act that would apply to gas plants, not their operation, but the fact that they left historical impacts to a site. And so it was the Superfund process that originally highlighted manufactured gas plants as being sites of interest for remediation. Very few of these plants presented imminent hazards. Remediations were required. They were usually done in a voluntary action by the company working with the state. And they wanted to put these properties back into productive service. And typically what you found is that there were these solid residuals, the ashes and the clinkers and the tars, and they typically would have to be removed and disposed of off-site. You would do groundwater treatments and remediations. And in the end, most of these sites have been able to be put back either into industrial service for residential use as well.
As the nation began to clean up the environment, the United States was hit by a shortage of energy.
You cannot have an economy functioning without energy. Energy is required to make the wheels go round in the economy, but the relationships have changed over time. With the Industrial Revolution, the energy requirements increased a lot.
Energy security, as we learned in '73 oil crisis, is very, very important. There are many geopolitical conflicts really based on energy or lack of energy.
In the 1970s, domestic oil production was declining, and natural gas was in short supply. Both resulted in high fuel prices. Industry and policymakers began to reconsider how we use these feedstock fuels.
We had large, secure domestic supplies of both coal and uranium. In 1978, the U.S. Congress passed the Industrial Fuel Use Act. This law was aimed at ensuring the flow of electricity.
The federal law said that new power plants had to use coal or alternate fuel to generate electricity. They wanted to save oil and gas for more important uses.
And then the accident at 3 Mile Island took nuclear power off the table. So with few locations left for hydro, that left coal as the only practical choice for new power plants.
By the time the Fuel Use Act was repealed in 1987, a fleet of modern electricity generation plants, complete with air pollution controls, was under construction in the United States. These are the coal-fired plants that provide much of our electricity today.
And the amount of coal used for making electricity continued to grow, even as the share of generation from natural gas and nuclear energy increased. As all those other energy sources developed, coal didn't go away. There's more coal being burned than any time in history.
In just 40 years, global energy demand had grown by 3.5 times. By 1990, the fully industrialized countries, 1/5 of the world's population, were using half the energy on Earth.
We are also living in a globalized world where many countries are catching up with us now. They want to have all the things that we have, so they actually expand their energy consumption a lot. China is one of the really rapidly growing economies. You can say that what took very long time in Europe to do happens in a very short period of time now in China. They use a lot of coal, mainly then also for electricity production, but also for heating purposes in industries and so on.
For rapidly emerging economies, providing energy is a top priority.
The single biggest issue is access to energy. These are countries that don't have the infrastructure that we have here in our country. So many of the people in those countries live in energy poverty.
Energy wealth from fossil fuels drove the Industrial Revolution. Now, rapidly emerging nations are using their domestic energy resources to build their economies.
The largest coal reserves in the world are in Russia, the United States, China, and India. Not surprisingly, those are the countries that burn the most coal. There are lots of advantages to the burning of coal. It has a very high energy density, meaning you get a lot of energy out of it. You can make a lot of power with coal. It's easy to transport, it's safe, it's stable, and it's cheap. This is why the modern world has been built on coal.
China and India, with close to 2.5 billion people, with a huge demand for energy, that energy will be supplied by the most accessible and the most affordable fuel that those societies have to access. And that's going to be coal. It will be for the foreseeable future over the next 50 to 100 years.
In the past, burning more coal has led to environmental consequences that were solved with technological improvements.
People still have this picture in their mind of a Dickensian coal plant belching pollution into the air. We have done a very good job in the developed countries of managing pollutants like sulfur, like nitrogen, like mercury, like ash, like particulates. The United States has successfully reduced criteria pollutants from power generation by roughly 90%. Now we face the next challenge, which is carbon. That one will be much, much harder.
Any fuel that came from living matter, coal, oil, natural gas, or even wood, they all contain carbon. When you burn that fuel, you get energy, water, and carbon dioxide.
Carbon dioxide emissions are a global problem. What happens anywhere in the world affects everybody else in the world because we all share the same atmosphere.
Humans have burned a lot of fossil fuel, especially coal, since the Industrial Revolution began.
Europe's carbon emissions, of course, increased a lot when they started to combust coal on big scale. So their carbon emissions continued to increase also with oil consumption, so it increased up until roughly 1970s. But after that, there has been actually a decline in carbon emissions in Europe.
The United States has also seen a leveling off of CO2 emissions as manufacturing declined and because we have retrofitted some coal-fired power plants to burn natural gas. In countries like China and India, as those countries' economies develop, they need more electricity. They're turning to the exact same place we turned in the 1800s in the Industrial Revolution. They're turning to coal. That's because coal is readily available, it's cheap, The technologies are there.
75% of China's electricity is from coal. 70% of India's electricity is from coal.
Clearly the increase into the future of carbon emission is going to come from developing economies like India, like China, like Southeast Asia. A quarter of that population doesn't have electricity. They have the right to have electricity. So it's tough for us to ask them to clean up something where they haven't even got the minimum standards we regard as normal.
Demand for energy globally is expected to increase by more than 50% over the next 40 years.
Today, over 75% of the world's energy comes from fossil fuel. Over the next 40 years, there will continue to be 75% of the world's energy supplied by fossil fuel. That says that there'll be a tremendous amount of renewable energy deployed, certainly, but that fossil energy will continue to be the dominant force. Is CO2 a contributor to greenhouse gases? I believe that it is. Should it be mitigated? Certainly. We need to have good coal technologies that bring economic benefit and bring a sustainable footprint for the future. Those are the kinds of technologies that are going to make the biggest difference in this world's environmental footprint.
We've seen amazing technological innovations in other parts of the economy that have really reshaped what we know is possible. There are going to be innovations ahead of us that none of us can yet foresee. We don't want to compromise on our ability to access energy or to use energy, but what we also want to make sure is that we're doing it in a clean, low-carbon, environmentally responsible way.
Today, coal is used mainly for electricity generation around the world and in the United States.
We need to focus on electricity because electricity is the main thing that we make with energy. 40% of our energy use is used to make electricity. And transportation is actually a significantly smaller portion of our energy use.
What technologies might help America and the world have enough electricity without CO2 emissions?
Wind energy is a very good resource where the wind blows a lot. The cost of wind energy in many places is now competitive for power generation with any other clean energy supply. It is domestic and secure, and the fuel costs are zero.
The most recent statistics indicate that wind provides 6% of the U.S. electricity supply and 4% of the world's electricity.
With technology and how it's evolved, we can get electricity just by putting photovoltaic panels on the roofs of people's homes. That requires a different kind of distribution grid, one that's able to take power as well as deliver it.
The most recent statistics indicate that solar provides about 1% of the electricity supply, both in the United States and globally.
The challenge with solar and with wind is they are intermittent. When the wind isn't blowing, when the sun is down, you don't have that power. And the intermittency can be quite dramatic. You can lose 80% of your solar in just a matter of minutes. It can come back in a matter of minutes too, but that creates challenges to the grid. That intermittency means that you have to back those energy systems up with other kinds of energy, often nuclear, gas, coal.
The way that our grid is set up is that we are forced to basically make almost exactly the same amount of electricity as we use at any given moment. You have to have an almost perfect balance between electric supply and electric demand, and if that gets out of whack by even fractions of a percent, you're going to get blackouts.
So for every kilowatt of intermittent power that we have on the grid, we need a backup system. You're doubling your capital costs because you have a backup system. That really is a big problem.
There's a lot of potential in solar and wind. We are, in fact, investing less worldwide in energy research, in developing more efficient, more powerful solar and wind technologies than we were in the 1980s. We're also behind in improving our transmission systems and our storage systems so that we can use those technologies as baseload power, as 24/7 sources of electricity, as we use coal today.
Electricity storage to me is the holy grail. If we had good storage systems, if we had battery systems that they're working on, it's really going to make a huge impact on our energy needs. But right now, the technologies are inadequate. Batteries are inadequate.
What it means is you have to start changing the way the grid works so that we can move towards that future where the intermittent sources aren't going to affect the grid in a negative way.
The good news is that it's a combination of new energy technologies and new information technologies, sophisticated enough to enable us to manage these new electricity flows that are opening up all sorts of possibilities for a smarter, cheaper, more reliable electric system, and one that's cleaner.
Infrastructure change on the scale that we're talking about is a slow process. And without the infrastructure change, we can't just shut off the fossil fuels and expect to have all of the services from electricity that we rely on right now, because we just don't have the tools to do that.
Right now, only a third of our domestic energy comes from carbon-free energy sources. But most of that is nuclear energy. The rest, nearly 2/3, comes from fossil fuels, mostly coal and natural gas.
In the meantime, the climate problem, the emissions problem is serious enough that we need to deploy these clean coal technologies that we already have, and we need to start putting them on commercial scale coal plants and using them to keep carbon out of the atmosphere, because we're not there yet with renewables.
Clean coal technology means that you are using coal without putting pollutants into the atmosphere. We capture essentially everything. Carbon capture and storage is an important part of clean coal. It's just one of the many things we have to do to have low carbon energy.
Carbon capture and storage is a group of technologies and techniques that enables the capturing of CO2 from various sources, the transport of that CO2, and then the final storage of that CO2 in deep geological formations underground. The capturing of CO2 can be done from power station flue gases, various flue gas streams in the steel and cement industries, as well as chemical industry or natural gas production industry.
CO2 capture technology has been keeping carbon dioxide out of the air for years at the Great Plains Synfuels plant in Beulah, North Dakota.
DGC was born during the time when natural gas was scarce in the late 70s, early 80s, and it was really an idea that was generated by a number of gas companies. So they saw a real win-win situation where this region had virtually hundreds of years of coal available in a shortage of natural gas, and a technology like gasification that could convert lignite coal to natural gas efficiently and provide that energy to the customers for home heating, for energy generation, those sorts of things. The coal reacts with oxygen and steam to generate a raw gas. From there, that raw gas is separated into liquid products and gas products. We're able to separate CO2 through what we call the Rectisol process. And that generates 95% CO2 and very little other contaminants. We compress that CO2, pipe it to Canada, where they're using it for enhanced oil recovery. We surpassed 30 million metric tons of CO2 that was sequestered in the oil fields in Canada.
Because of the nearly pure CO2 stream, CO2 capture works well at the coal gasification plant. Not so with traditional power plants, where the CO2 makes up less than 15% of the emissions. They need a different separation process to remove the CO2 from the exhaust, which is mostly nitrogen.
What we need to do is separate the carbon dioxide out from the rest, so we don't want to put all that nitrogen underground. So that's why you need the separation step, which is expensive, but it makes the transport and injection of carbon dioxide much, much more efficient.
This technology is key for the hundreds of existing power plants that currently make a third of the electricity in the U.S. and more than 70% of the electricity in China and India.
Even with the low CO2 content in the exhaust, carbon capture has become a reality at the Boundary Dam Power Plant in Saskatchewan.
Our government wants to reduce its greenhouse gas footprint. We had to answer the question ourselves. Does coal remain in our fleet as a fuel supply to generate power? Can we keep coal in our mix, or do we start looking at abandoning our mines and moving perhaps to natural gas? So it to me is a very important project. It's a very low emission plant. It's the world's first plant to demonstrate the cost of capturing carbons. What's really going to be significant for us is to have the actual economics of this plant show us at SaskPower that we can capture carbon into the future and reduce greenhouse gas emissions. I think it's significant for other countries or companies to also see this data so that they can make their own decisions. This model, it can be really transferable around the world.
What does the commercial success of carbon capture at the Boundary Dam Power Station mean to coal and to electricity generation?
Carbon capture and storage will have a strong role globally only if both the United States and China truly embrace the use of this technology. They are the two biggest economies, the two biggest CO2 emitters, and they really have an enormous stake in getting CCS right.
We have the technology to do it, but right now it's very expensive. And so there's always this give and take between the cost of energy and how clean the energy is. To clean it up takes money. And as energy prices go up, there's a negative effect on our society of that as well.
What we need is to spend some money. There's investment tax credits and production tax credits for wind and solar and other kinds of clean energy. We need to open up the markets to make policies that support clean energy of all kinds. We want to finance wind plants, we want to finance solar plants, and we want to finance clean fossil plants. And clean means near zero emissions, period. And if we don't do that, we're placing our planet at risk. In the United States, a third of the plants will probably just shut down. A third of the plants are viable for retrofit, and a third of the plants are on the bubble. But some of the plants will be retrofit, and that will be good for America.
It's our responsibility to use our resources in a wise manner. We have tremendous reserves of coal. It's a perfect fuel for baseload electrical generation. To take that off the table is irresponsible. Let's do that science and engineering it takes to use that coal in an environmentally responsible manner.
The move has to come from the older industrial nations, the United States, Europe, Australia. They can develop the technology, make that technology established, and then the developing nations will pick that up and make that much cheaper. But we have to make the first moves.
Through time and waves of technological change, we have learned that energy is critical for economy and quality of life. The world now uses 20 times the energy it did in 1800, and life has improved dramatically in the post-industrial world. Coal laid the foundation and continues to play a critical role.
Does coal likely have a future? I think it does. Coal is so abundant in the United States, there's so much of it, we'd be foolish to not try to utilize it in some way. But it's finding a smart way to use it that I think is the real challenge.
That, in fact, is part of the purpose of carbon capture and storage, that the world can carry on using coal and add on a few percent only to the cost of using that fuel, but make that fuel environmentally clean enough that we can carry on using that for the next 40 or 50 years. It buys us time to develop new, even better methods of capturing carbon and new, even better methods of generating zero carbon electricity.
We're not talking about either clean coal, advanced coal, or renewables. We're talking about ands, where we have to use every clean energy source that we know of in order to solve our carbon problem while also providing billions of people on Earth with something that looks like a modern life.
As the world's population grows, that's becoming increasingly difficult, and the strains on the environment are becoming more intense. So, in order for our children and grandchildren to have the same quality of life, we need to continue to develop those technologies that will allow us to use coal, yet spare the environment the negative consequences.
Funding provided by the U.S. Department of Energy, Office of Fossil Energy, the National Energy Technology Laboratory, members of the Energy and Environmental Research Center's Plains CO2 Reduction Partnership, and the members of Prairie Public.